Hey guys, it's Pete Moncrianis, and I'm going to be doing a tutorial on how to do problem number 35 on page 49 of the textbook. So this is the train problem, and so first thing we're going to do, jump right into it, and we are going to read the question. The train is traveling down a straight track at 20 meters per second when the engineer applies the brakes, resulting in an acceleration of -1 meters per second squared, as long as the train is in motion. So that's a key part. We'll come back to that. How far does the train move during a 40-second time interval, starting at the instant the brakes are applied? Alright, so first things first, we gotta draw our picture. As you can see here, I got a beautiful little train. And we want a starting point. So I'm going to put the start point at the front of the train, for example. So that's where, in our question, in our theoretical experiment that we're putting together, where we are visualizing this train going down a straight track. So that's its start point. And that doesn't mean it's like starting from rest. No, it's actually just where this problem puts us at that instant. So we know it's traveling down a straight line, so we can definitely go ahead and put that line there, showing that it's traveling down a straight line. And we want to make this direction positive because it is moving forward, right? So we're going to identify that if it's moving to the right, in this case, it's going to be our positive direction. So now we have a start point, and it says the train is traveling down the track 20 meters per second, and then the engineer decides to apply the brakes. So we'll put a point like right around here. Until that point, our train is moving 20 meters per second. And at this point, it starts accelerating at -1 meters per second squared for an interval of 40 seconds. So what that means, interval of 40 seconds, is given 40 seconds in the future, like if we are here right now, moving 20 meters per second, and all of a sudden I know that I'm the engineer on the train, and I hit the brakes. In 40 seconds, how far will I have traveled? So that's going to actually be this distance from here to wherever it ends up is going to be what we're looking for. So first thing first, let's assign our variables. Velocity final, we actually don't know yet, and I'll explain that in a second. Our initial velocity, we know, is 20 meters per second. Our acceleration, given to us here, -1 meters per second squared. So it's just decelerating, right? The train's slowing down. And after that, we need time. We know we have a 40-second interval, but that actually is not our time that we're going to be using in our equation. And the last thing we need is displacement, or how far the train has moved. And so that's what we're going to be solving for right here. That's what we want. So that's why a picture helps. Sometimes it shows you, it really like narrows down what exactly you're looking for, sets the stage, this way is positive. Without that, you wouldn't know, and you wouldn't know which way you're actually heading, even though it's a straight line. So I mean, you can infer it knowing that this is negative, but this definitely helps to say that negative means that the acceleration is pushing this way, so it's trying to stop the train from accelerating. So a key part in the book that it says is it'll decelerate at this rate, at a constant rate, until the train has no motion. Right? It's as long as it's in motion, this acceleration will apply at a constant rate. But until when the train stops, it will you will stop decelerating, right? Because if you're driving a car down a road and you hit the brakes, when you come to a complete stop, you're not all of a sudden just going to start reversing. You're going to be staying there for the duration of the time that is allotted. In our case, it's 40 seconds. So what we actually need to do is 40 seconds is kind of our domain, our maximum. So we want to see, it's like our viewing window of how much of the graph we get to see. So what we want to do is actually find out how many of these seconds it takes for this train to stop, or if the train even stops at all during this 40-second period. So I'm going to test for 0. And this is a pretty simple equation that I came up with when I was doing this problem. So I want it to end up at 0 meters per second to see. And if it doesn't equal 0 meters per second, I know that the train traveled, that the train did not completely stop during my 40-second interval. So 0 meters per second equals 20 meters per second is how our current velocity at this instant right here, plus our acceleration. So acceleration is meters over seconds squared, but another way to do it is -1 meters per second for every second that goes by. times, I'll put t as our variable time. So what this is saying, for every second that goes by, we slow down, our velocity decreases by 1 meter per second, or we add -1 meters per second. So this equation should look familiar. It's actually where we get our original equation from, which is velocity final equals velocity initial plus acceleration times our change in time, right? Velocity final, velocity initial, acceleration, change in time. So that's where that comes from. So that was a little neat thing that I found, that when I was looking for this final velocity, it's actually just the same equation. So even if you didn't know the equation, didn't have the equation, you'd still be able to solve this problem. So I'm going to go back, plug in everything. Excuse my dog in the background. 20 meters per second plus, and this time I'm just going to write it as meters per second squared, now that we've explained what really acceleration does and how it affects our problem, times our change in time. And we will solve for our change in time. So -20 meters per second equals -1 meters per second times our change in time, right? Just move that to the other side. And now we are going to find that our change in time is 20 seconds, right? Because this is meters per second squared. One of these seconds cancels with that second. When you divide, reciprocal of the units, and our meters would cancel as well. Negative divided by negative makes a positive, 20 seconds. So now we can actually go back here and we can cross out this 40 because that was the domain that we have, but we know that our train is only going to be traveling for 20 seconds. After 20 seconds, after it hits 20 seconds, it's just going to be sitting here. It's not going to move for the duration of the 20-second interval, or the 40-second interval, which we have 20 seconds left. So now we're going to actually solve what the problem is asking for. How far did the train go? So what we're going to do is we're going to take our equation from our equation sheet and find which one has what we need. So I'm going to take equation 2 right here. Some of the other equations would have worked as well now that we have more variables, because we know that we will stop, so our final velocity is 0 meters per second. So I'm going to take equation 2, which is delta x equals 1/2 times the initial velocity plus final velocity times the change in time. I'm going to plug in my variables. Delta x equals 1/2 initial velocity 20 meters per second plus final velocity 0 meters per second times the time 20 seconds, not 40 seconds. So once we simplify this, we end up getting delta x equals 200 meters, right? Seconds cancels with seconds, right? You're left with meters. 0, there's no units for 0, so we cross that out. Oops, sorry. Right? And we are left with 200 meters, right? So what happens is, if you took this 40 seconds that was given in the problem and used it for this change in time here, your total would have been 400 meters, double what it actually is, because our train is only moving for 20 seconds, but by putting in the 40, you're saying that it's continuing motion for 40 seconds, which would be incorrect. So that's why we had to find out what the true change in time was. So yeah, it's really important. The important things about this problem is that you notice that it says in the problem, it's decelerating or accelerating at -1 meters per second squared for until as long as it's in motion, and once it stops, it stops. So then you also have to realize that this is a 40-second interval, so it's not actually the time that it's going to take to reach its final velocity, and that's what we wanted. And the last big thing, or last two big things, is always define which way is positive, so that we know that this is a negative acceleration pushing the train this way. But once the train stops, it's not going to actually reverse. It comes to a complete stop after 20 seconds. And the last thing is acceleration. Now that we know that acceleration is just a fancy way of writing your velocity will decrease by, or increase, depending on the problem, but in this case decrease by 1 meter per second every second. Because isn't that the units for velocity? It's the same as the units for acceleration over seconds per second. And that's why we use time here to tell you how many seconds it'll take until we reach 0 velocity. And yeah, that's that. So final answer, 200 meters.